Hi guys, this is our lecture on chapter 11. This chapter is extending some of the discussion we've already had in chapter 10 on risk and return. We know some investments increase risk, but what exactly is risk? And this chapter really goes into more specifics on that. There could be courses devoted to just these topics. So in a lot of ways, we're skimming the surface. In this chapter particularly, it's very in-depth. So we're not going to get through quite everything in this class. We're actually going to go through a couple things next week from this chapter. So don't be surprised if we stop. We're going to stop right around the CAPM beta when we start getting into that stuff, the security market line. So take note of that. I think you should read the entire chapter, but we're going to get moving. And by the way, my battery might run out, so I might have to stop. It just might shut off randomly. All right, so what are the key concepts and skills from this chapter? You want to know how to calculate the expected returns. You want to understand the impact of diversification, the systematic risk principle, and the security market line, and the risk-return trade-off. Here's how that chapter is outlined. All right, so last chapter we really got into the history, and this here we're getting into future or expectations, expected. So the thing we start off talking about is expected returns. Expected returns are based on the probabilities of possible outcomes. So you have your expected return here on the left-hand side of this equation. Then you have a summation of P times R. What's P? P is the probability of state I occurring, whatever that state may be. And R is the expected return on an asset in state I. So let's give an example. Let's say you have three different states of the world: recession, neutral, or boom. And there's a probability of each. There's a probability, 25% probability that we're going to experience an economic boom, 25% probability recession, and then maybe we'll just be standard and stay flat. That's 50% probability. So you have two different stocks, and one's a counter-cyclical stock. In other words, it does better in recessionary scenarios. You might be wondering what something like that might be. Collections agencies, for example, do actually pretty well during recessions because they have more demand for their products. So maybe that would be stock B. Stock A is a typical stock that moves with the economy. So you can see expected returns for each. For stock B, they do better during the recessionary scenarios and do worse during booms. Stock A does better during the boom and worse during recessions. So how would you go about calculating your expected returns? Well, it's pretty straightforward. You would multiply your probability by your expected return. That would give you negative 5% in this case. Probability times 15% here gives you 7.5. 0.25 times 35%, 8.8. Then you sum them down for each. And the interesting thing here is the expected return for stock B is actually larger than stock A. You have a 12.5% for stock B. So stock B looks better overall. Variance and standard deviation, as we already discussed, measure dispersion of points around the mean distribution. In this context, we're attempting to characterize the variability of possible future security returns around an expected return. So in other words, we're trying to quantify risk and return. Variance and standard deviation measure the total possible or the total risk of possible returns. So it's important to point out that these formulas are for forecast data and thus use probabilities to weight possible future outcomes, unlike the formulas in Chapter 10 that were using historical data, as past outcomes are equally likely. So variance and standard deviation measure volatility of returns. Variance is going to be your weighted average of squared deviations, and standard deviation is the square root of variance. So you guys are going to see we're going to get a little bit into this calculating variance and standard deviation, which we did in the last chapter. I advise you can go ahead and click on that Excel down in the lower right hand corner to get all this information in Excel, and it may help you as we go through this. So you use Excel to break it down, but you can go ahead and actually calculate out variance and standard deviation using all the information that you've acquired, for stock A and for stock B. Let me click over to that real quick. Sorry. Oops. Okay, so getting the variance. Hold on just a second here. Hold on, bear with me for a moment. This is why I didn't want to show Excel. I know it would mess up the picture. So you can go ahead and click on Excel, and you can go into the various cells to check out what's in there, and how you go about calculating everything. I'm not going to have an opportunity to really do this in an easy manner going through Excel, so I'm going to stick with the PowerPoint. So take some time to dig through that, and if you have questions about how to calculate standard deviation and variance, just let me know. I'm hoping that statistics would have covered most of this, as it should, but if we need to go over it again in class, that's fine too. All right, so that's standard deviation and variance. And of course, I'm sure you've all heard of, and in a sense you kind of already are using these portfolios in whether it be retirement planning or just even our stock simulator game. A portfolio is a collection of assets, and an asset's risk and return impact how the stock affects the risk and return of the overall portfolio. The risk and return trade-off for a portfolio is measured by the portfolio expected return and standard deviation, just as individual assets. Now, like I said at the beginning of this chapter, we're skimming the surface here. There's courses devoted to portfolio theory, so we're going to get into this a little bit, but not terribly in depth. All right, so getting into portfolio expected returns. The expected return of a portfolio is the weighted average of the expected returns for each asset in the portfolio, where you have weights, which we have here it's symbolized as WJ, and that's the percentage of the portfolio invested in each asset. So in other words, you're going to sum out the weight and expected return. So you have expected return of some particular investment, then the weight of that, and you sum them all the way across for the entire portfolio in order to get your expected return for the portfolio. So a quick example, let's say you have assets A, B, C, D, and E. You have a certain amount of dollars invested in each, and there's a percentage of your overall portfolio invested in each, which is pretty straightforward to calculate. You can actually calculate this 30% by going 15 over 50,000. So you can actually calculate the weight. So you also have an expected return for each individual asset, and in order to obtain this number over here, you're simply going to multiply the 30% times 12%, and you get 3.735. You do that all the way down across all the assets, and then you sum them down the bottom, and you get your 10% overall. So that's the expected return for the portfolio. So the expected portfolio return also has an alternative method. The alternative method takes a different approach by calculating expected return in the portfolio in each state of the economy, then applying the probabilities to again arrive at the portfolio's expected return. So it's doing something similar to what we just did, but it's also taking into account recession, neutral, and boom, which complicates things. Now, I believe that let's just click back real quick. Yeah, you still have your original stock percentages, 30%, 17%, 22%, 20%, and 12%, overall 100% of the portfolio. But now you're splitting up those expected returns based on probabilities of recession, neutral, or boom. So the steps are to calculate the expected portfolio return in each state, which you're going to do first. So you would do that across. So for example, the portfolio return in a recessionary state is 3%. I'm sorry, negative 3%, 13% for neutral, and 17% for boom. These numbers are taking into account the row across that it's correlated with. If you then apply the probabilities of each state to the expected return of the portfolio in that state, and then sum these up, you end up getting 10% overall, which is exactly what we obtained in the previous. So the bottom line here is that you could go about doing this utilizing those recessionary, neutral, and boom states as well. And now we're finally getting a little bit into diversification, because we're talking about here portfolio risk. Portfolio standard deviation is not a weighted average of the standard deviation of the component securities risk. If it were, there would be no benefit to diversification. Combining securities into portfolios can reduce the variability of returns, which is what diversification is. All right, so portfolio variance. There's 3 steps to going about calculating this. First, you compute the portfolio return for each state of the economy in our case. Then you're going to compute the overall expected portfolio return using the same formula as an individual asset. And then finally, you're going to want to compute the portfolio variance and standard deviation using the same formulas for an individual asset. So, giving you an example, sorry about that. Giving you an example, the negative 3, 13, and 17 percentages here were already given. We can obtain that DEV here, the deviation, by simply negative 3% minus the expected return, which is not shown here, of minus 10%, is going to give you a negative 13. And 13%, for example, minus 10% is going to give you 3%. 17 less 10 is going to give you 7%, and so on. Then you square that deviation in this next area here, and finally you multiply that by the probability in this final column. The variance is then just simply the summation of these, and the standard deviation is the square root of that number. So that's how you would go about calculating portfolio risk. So another question is, so we talked a little bit about portfolios and portfolio risk. Another question here that's interesting